The objective of this video is to learn the reactions of radicals. Now the name says it, radicals. They are very highly active. So these radical reactions are very rapid, vigorous reactions, and they can be kind of out of control. So they are not the actual, they are not an ideal type of reaction if we are considering synthesis reactions. You will see why we don't consider the radical reactions in terms of multi-step synthesis when you examine the reaction mechanism of radicals. So far you have learned different types of hydrocarbons, to name few: alkanes, alkenes, and alkynes. Now if you consider alkanes, all you have is just carbon, hydrogen, and all single bonded carbon structure. Now these are the alkanes. You have only single bonds. And then alkenes, you have double bonds. Alkynes, you have triple bond. So these alkenes and alkynes, they have some level of unsaturation. So there can be certain reactions done on alkenes and alkynes. You have looked into those reactivities and you see there's a large number of reactions you can do with these multiple bonds. However, since alkanes, since they are holding only these strong sigma bonds, just single bonds, these molecules are completely saturated in terms of bonding. You don't have any unsaturations like this multiple bonding. So it is really hard to do other chemical reactions without using any other catalyst. In addition to combustion, the only other type of reaction you can do on alkanes is the radical reaction without using a catalyst. You can do some reactions on alkanes, but you will always need a catalyst. However, the only reactions that you can do without a catalyst is the combustion, meaning burning reaction, or the free radical reaction. And today we are going to look into the free radical reactions. Now these alkanes are also called as paraffins, derived from a Latin word meaning little affinity, because of this really low reactivity due to the saturation. Most of the alkanes, you have seen that you don't see any multiple bonding. All you see is just carbon-carbon or carbon-hydrogen single bondings throughout the whole structure. However, if we provide a halogen either with high heat or with high radiation, so this radiation is indicated by H nu. So we need to provide either high temperature or suitable wavelength, a radiation with a suitable wavelength, to make this radical reaction happen on a given alkane. Otherwise, alkanes are really unreactive. Without giving these conditions, we cannot get an alkane halogenated. And you know by now that alkyl halides have a lot of reactivities. If we can get alkyl halides prepared by some method, we can subject them to many multi-step synthesis processes. One way of generating these alkyl halides is radical reaction. However, radical reactions are not the ideal way to generate alkyl halides. So far you have done reaction mechanisms and you are very familiar with this arrow with two barbs. This means a heterolytic bond cleavage, meaning in a bond you know that there are two electrons. So this two barbed curved arrow means both of these electrons are taken by one of the atoms in the bond. That means these electrons are unequally distributed upon breaking the bond. one atom take both electron and the other atom is left with nothing. So the atom that takes both electron takes the negative charge, and the atom that doesn't take anything assumes a positive charge. Now these are the most commonly used ones in all these reactions you have done so far. However, in radical reactions, we use homolytic bond cleavage and use these kind of single barbed curved arrows to show the homolytic bond cleavage, meaning that the two electrons in this bond are equally given to the contributing atoms. So each atom will have a single electron, an unpaired electron. And these kind of species are what we call as radical. Why? An unpaired electron is kind of unstable. It is an incomplete octet. It will try to somehow reach stability. That is why radicals have a very high reactivity. Radical reactions, we have three main steps. The first step is initiation step. In the initiation step, we are actually generating the radical. How do we generate that radical? Either by giving high heat or radiation with suitable wavelength that will subject the halogen into a homolytic bond cleavage, resulting in the two free radicals. After the initiation step, what comes is the propagation step. Now this propagation step, in some contexts, it is called as a chain reaction. And also, sometimes it's referred as radical substitution reaction. So in the propagation step, what actually happens is that, as the name says, the reaction propagates. It keeps on expanding. How does it expand? By creating more and more radicals. So in the propagation step, you will see some products are made, and in addition to the products, it will keep on making more radicals. It is this making of more radical that leads to the propagation of the reaction. Why? Now these radicals keep on colliding into more and more other molecules, and it results in a chain reaction. So you can see why this propagation step is also called as a chain reaction. And why do we call it as a radical substitution reaction? Just check here what is happening. Over here you find a chlorine radical. If you count the number of electrons, you will see that there are only 7 electrons. There is this one unpaired electron. So this is acting as a radical. This radical go and collide with CH4 molecule, and you can see it is going to steal a hydrogen from the CH4 molecule, leaving a CH3 radical. And then the CH3 radical goes and collide with a Cl2 molecule. Now this is a Cl2 molecule. Over here CH3 is the radical. Once this CH3 radical collide, what you get is a monosubstituted alkane. So this is a single chlorine atom substituted into CH3. So what ultimately happened is that this Cl replaced a hydrogen. So that is why we call it as a radical substitution reaction. A radical at the end gets substituted in the place of a hydrogen. The last step in radical reaction is what we call as determination step. In the termination step, what happens is that all the radicals get neutralized. As long as we find a radical, the reaction will keep on going as a chain reaction. So in order to stop the reaction, we actually have to collide a radical with another radical, and there are many possibilities. If a chlorine radical collide with a chlorine, you end up with Cl2. If three methyl radicals collide with each other, you get ethane. And if a chlorine radical collide with a methyl radical, you get methyl chloride. So you can see in the termination step, you don't find any radicals. You have only neutralized species. And you can see you can end up with a variety of products from these free radical reactions. All right. So how do you think you can control the amount of product you get from a free radical reaction? For example, if you want only a single substituted alkane, for example, let's say if this is what you want to get, how do you think you are going to stop the reaction at this point? First of all, it is quite hard. Why? The free radical reactions are highly reactive. They are kind of out of control. So it is really hard to control this reaction. The only way we can get this single substituted product is by adding more of the alkane. So that means if you want to get this product more, you have to keep on adding methane more and more into the reaction mixture. So that way there is more probability for chlorine radical to collide with methane instead of other species. The only thing we can do is add this to increase the probability to get the desired product. Otherwise, the radical reactions are quite out of control. They can keep on making more and more substituted product. For example, once you get the single substituted product, a radical can collide with that, and now you can have another radical which can be led to a disubstituted one. And if you really think about the propagation of the reaction, you can continue with this too. This disubstituted one can get into a trisubstituted one. So the only way we can have the desired product is by controlling or adding the desired substrate to the reaction mixture and increase the probability of collisions. Now the first mechanism we looked into was between chlorine and methane CH4. Now we are going to look into the mechanism of this radical reaction with bromine, and our substrate, the alkane, is C2H6 or ethane. Now this is a 2-carbon compound. The first mechanism we looked into was just single carbon molecule. Now again, you can find the same steps. It doesn't matter what kind of alkane you use. For every free radical mechanism, what you have is these 3 steps. So from all of the reaction mechanisms you have done so far, I think the radical reaction mechanisms are the easiest. So in the initiation step, you get the 2 radicals. The radicals go and collide with the carbon-hydrogen bond, and it keep on generating certain products and the free radicals. In the termination step, you can see the radicals colliding with each other to make different products. The relative stability of different radicals. The radical stability go as you see here. The tertiary radical is going to be the most stable form and the methyl radical is the least stable. The reason for this trend in stability is due to a concept you already know, hyperconjugation. By now you know carbon doesn't like negative end on it. Having this single electron is a big pain for this carbon atom which doesn't like to hold on to that many electrons. Why? Because carbon is not a very electronegative atom, and because of that it doesn't like these negative charges and it want to dilute this negativity that's set upon this carbon. How does it do it? Through hyperconjugation. So hyperconjugation is a way that this negative electron cloud is diluted. However, in order to do it, it needs more carbon-carbon bond. Having a hydrogen carbon-hydrogen bond is not helpful. Why is that? If we think about the methyl radical, you have carbon and then where is this radical? You have this p orbital and your radical is sitting like that, and what you have is hydrogens. What kind of orbitals does hydrogen have? They are s orbitals, spherical. Now let's move on to primary radical. Think about the hyperconjugation. What it has is it has hydrogens, carbon hydrogen, which has s orbitals, and then this means it has this adjacent carbon. Now what kind of bonds do alkanes have? Alkanes have sp3 type hybridization. So these orbitals are going to be sp3 type hybridization. Now if you have a carbon right next to this carbon holding the radical, you can assume you are having these sp3 orbitals. Now these orbitals can overlap and dilute this negativity, and by that way it helps to stabilize this radical. The more and more you have carbons attached, the better this overlap is. If I draw the secondary radical, you have the carbon and here you have the p orbital holding the radical, and then you have hydrogen which has s orbital, and then you have a carbon here which has these sp3 orbitals. Now it can overlap like this. Now I'm drawing this other carbon. Now this is a better way of diluting this negativity compared to the previous one. Think about the tertiary radical. You have the carbon, the radical, and you have all carbons around it. Now these can be diluted in all directions. So that way this radical is more stabilized through hyperconjugation. So the more substituted groups you have on the carbon holding the radical, more stable it is going to be. Now we are going to look into the radical reaction in a compound that has more carbons. The previous two examples we did were CH4 and C2H6. So if you are doing a radical reaction to something like CH4 or C2H6, there is no much difference. In the first one, just one carbon, and in the second one, you have only two carbons. The radical can come and attack the first carbon or the second carbon. It really doesn't matter which one is which. But you will start seeing certain changes when the number of carbons increase, like when the number of carbons come to a level of 4. So let's take butane. Now when we take butane, there are two possibilities how this chlorine radical can come and attack. It can attack either this carbon, the first carbon, or the second carbon. It can go and attack the third carbon, but it again means the same thing as attacking the second carbon. Why? Just because it has only 4 carbons. Again, it can attack this one, but it is same as attacking this first carbon. So there are 4 possibilities if our alkane is butane. So considering how these hydrogens are located, we can expect that we can have 60% of 1-chlorobutane and 40% of 2-chlorobutane. Why we expected that? Because if you examine this carbon atom, you have 3 hydrogens that is exposed. So overall, you have more terminal hydrogens, and terminal hydrogens are more accessible than the internal CH bonds. So because of that, we expect there would be more terminal substituted ones rather than internal substituted ones. So how exactly we ended up with 60% and 40%? It's just by counting the total number of hydrogens versus the terminal hydrogens. What is the total number of hydrogens? You have 3 here, 3, 6, plus 4, that is 10. In butane, the butane formula is C4H10. So the total number of carbon is 10. And how many terminal carbons? You have 3 carbons, terminal hydrogens. You have 3 terminal hydrogens here and another 3 terminal hydrogens on the other end. So you have a 6 of terminal hydrogens. Take the percentage. You get 60%. That is how we ended up with 60% for the terminal substitution. And if you do the same type of calculation for the internal substitution, how many internal hydrogens you have? 4. So that is 4 out of 10 to 100%. You get this 40%. Right. So that is how we predicted to get 60% and 40%, 60% for the terminal one and 40% for the internal one. However, experimentally what we got is 29% of terminal and 71% of internal, which is quite the opposite we expected. How we ended up with this kind of experimental result is because of the stability of the radical that is made. Think about the alkane, and once you generate this radical from the initiation step, this radical can go and attack either the first carbon or the second carbon. If this radical decides to go and do the reaction and create a radical on the second carbon, what kind of a radical is this? Now this is a secondary radical. If this radical, chlorine radical, attack the first carbon, it will create a primary radical. Now the primary radicals are not stable as secondary radicals. The secondary radical formation leads to the internal substitute product, which is 2-chlorobutane. And the terminal radical leads to the 1-chlorobutane, which is the terminal substitute substance. So this experimental result relate to the stability of the type of radical we have created. The secondary one, even though we thought that these internal bonds are less accessible, actually they are not. What governs the reaction, governs the product distribution is the stability of the radical that is made instead of this the hindrance that we thought. Now we are going to compare the chlorination reaction versus the bromination reaction in radical reactions. If you take, just forget about these expected numbers, compare the experimental values. If you do the chlorination radical reaction and the bromination radical reaction, you can see that bromine has more selectivity in terms of products. In the chlorination reaction, it was 29 to 71% ratio, but in bromination, the internal substitute one is more preferred. What it means is that the reactivity. It has found that bromine radical reactions are less vigorous compared to chlorine radical reactions. Bromination reactions are slower compared to chlorination reactions. And in general, if the reactivity is higher, it has less selectivity. Since chlorine has a higher reactivity, it has hardly any time to choose between things, so the distribution is not that drastic compared to the bromination reaction. Since bromine has a lower reaction rate, it has some time to choose between things and it is going to be more selective. So in general, if you have a higher reactivity in any reaction, it will lead to less selectivity. So far we have looked into only chlorination and bromination reaction, and why don't we talk about any fluorination or iodination reaction? Now just look at the chlorination and bromination reactions and the energy, the amount of energy associated with the chlorination or bromination. So these are the two reactions that we have done so far. For chlorination, we have, this is cal per mole. You can see how these numbers go. And what does this sign mean? We are talking about this enthalpy. How much energy is associated with the reaction? What does this negative sign mean? Negative means it is releasing heat. The more negative the sign gets, more vigorous the reaction is. So that means the fluorination reaction is very vigorous. It is releasing so much energy that we are not actually doing the radical reaction with fluorine. Why? It's releasing so much energy that it can even be explosive level. So we actually don't do fluorination reactions with these fluorine radicals. And chlorine bromine energies are much controllable level, And if you compare the iodination energy, the energy associated with the iodination radical reaction, it has a higher value. So what you see with other energy values are the positive signs. If you have a positive sign, that means it's endothermic. You have to add energy. So that means you have to add so much energy if you want to get iodine reaction done. So this is not an ideal situation. Why? It needs high energy compared to chlorination or bromination reactions. So because of that requirement of high energy, we do not do any iodination reaction.